Good morning, Year 13s. I've sent you a quiz. Well, it's not a quiz, it's really a survey because obviously I'm finding it very difficult to know exactly how you're getting on. It's easy enough for the people I know are uploading work and completing the tasks on Seneca Learning, but I know some of you aren't and some of you haven't signed up to Google Classroom. So I am really, really concerned. You know, it is not too late to pull it back, but you know, if you're not doing the work, you can't progress. So I suspect that some of you are just have got a bit lost. So please, can you email me or send me the survey, and then, you know, at least I can do something, kind of think about it over half term and think about how I can help you, and you can think about whether to keep this subject on or not. And I strongly suggest, if you have fallen behind, there are 2 weeks. I'm not going to set you much in the way of work. Can you just take that time to catch up? This is your time. You're getting a breather. I'm not going to bombard you with more work. I don't think there's any point. I want you to just go on through and complete, you know, just go back over, just make sure, redo the questions, play some of the videos. You know, there's better videos than mine online. That Machem guy, he has all sorts of videos, the ones I sent out last night. So go to his YouTube page, but just, you know, save it now or else decide it's not for you, okay? But anyway, I am very willing to give you extra help if that's what you need whenever we get back. But you have to obviously work as well. Anyway, that said, if Mrs. Carher, kindly pause the video at this point and allow you the time to do that quiz, right? And then I'm going to work the questions from yesterday. Now, I know I'd said I'd post the answers last night, but I didn't do my homework, so I apologize. I'm going to work through it now, and you can correct as we go. And then hopefully, as I'm talking how I think about these, it might hopefully help clarify some of the ideas in your head. Right, so in order to complete this first task, you need to know the trends. You need a periodic table. You really, unless you've learned something off, which I really don't recommend. There's better ways to spend your mental energies than that. So on the periodic table, which I can't get my hands on. Right, so oxygen is more electronegative than hydrogen. So it's the more electronegative, right? The further to the right, the further up a group it is, and the further to the right in the period it is, the more electronegative it's going to be. So that's a delta plus and that's a delta minus. Sorry, oops, rather wrong way around. Delta minus, delta plus. Same here. SH, delta minus, delta plus. HCl, delta minus, delta plus. Very rarely that hydrogen isn't the delta plus end. It doesn't have much of a hang on to electron pairs. Delta plus, delta minus. This is the most polar bond that you can get. Okay, it's the most polar bond. And these two, followed by that one and then that one. Okay, HI. Now, I know, as I said, I think I mentioned it, they're very close in terms of their, you know, the electronegativity difference doesn't come out. It's very high, if I recall. But I suggest, well, I'll tell you in a minute. Give that's a delta minus, delta plus, delta minus, delta plus, delta minus, delta plus. And over here, delta minus, delta plus. So again, carbon is more likely to be the delta plus end of things. In fact, I can't think of a situation where it's not. I suppose if it was covalently bonded to a metal, but we're not going to have to worry about that. This is going to be the same, right? So the double bond doesn't make any difference. Now, so I want you to bear in mind that non-polar bonds, right? Assume that the non-polar bonds, the only ones are where you have two of the same atom. Okay, so non-polar bonds like F, Cl, Cl, it doesn't matter how electronegative the atom is. If it's bonded to another one of itself, it's just going to have completely delta, and the electronegativity difference is 0. And the only exception I want you to think about, right, it's anything at all, okay, etc., right? So you get that idea, do the same atom. The exception, right, and this will be really important when we do organic chemistry. is the CH bond. Now, I think it counts as being polar. This is a non-polar bond. Now, how I know this is when you were doing organic chemistry and these CH bonds are everywhere, right? They do nothing. They're incredibly dull. They don't bond. They don't participate much, right? They do the odd thing, but really they just hang around as on the sidelines. So they're de facto non-polar, despite the Pauling electronegativity difference of, I think, 0.4, okay, which would suggest it is. So that is the only non-polar bond you have to think about that's not just to the same atom. Now, what I would say for polar bonds is anytime you have two different atoms, right? And I wouldn't worry about calculating the electronegativity difference. Just assume if there are two different atoms covalently bonded, and it doesn't matter if it's double, single, triple covalent bonds. If you have covalent bonds and there are two different atoms, then assume it is a polar bond. Okay, so that covers everything, right? That would be how I would suggest, rather than thinking too hard about whether they're far enough apart in the periodic table, because it can be very hard to tell. You know, it's easy to tell if there's electronegativity difference between atoms in the same period or atoms in the same group, but not if you have, say, a period 2 group 5 elements like nitrogen versus chlorine or something like that. It's not always that easy to tell, you know, which is the more electronegative. So all I would assume is, for now, just assume that it's two different atoms. They're going to be polar, there's going to be a dipole, and they're going to be polar bonds. Now, I'll just mention maybe the idea of dipole versus polar bond. So I think I've mentioned this before. The polar is the adjective, so you're describing that it has a dipole. So polar bond means it has a dipole, okay? So that's what you're describing. Now, let's pick NH. Good old, very polar bond there. Okay, so if we want to indicate it's polar, we do that with a little delta minus delta plus. Okay, so that's how we indicate the two different poles. Now, the dipole moment is really a physics concept. It's to do with vectors. Now, I know I'll scare you. Some of you will go, oh yeah, it's vectors. And some of you will go, what? All you have to know about really is how you indicate it. So if you want to show this vector idea, right, this is, oops, it's the wrong way around. You put like a plus at the end, that's the delta plus, and then you have an arrow, which is kind of pointing at the direction of the electron density. So if we go over to, say, the C double bond O, this is like that. Are you supposed to do that for all of these? Yes. Okay, so I'll go back and do all these. Okay, so direction of dipole moment. I'm going to have to put it beside it. Although it's normally underneath, right? So it should really be here, but I think I've run out of space. Didn't give enough space. Now, sometimes they try to indicate by the fatness of the arrow which direction the dipole moves in, or how large it is, but I wouldn't worry about that. Okay. And obviously no dipoles here, no delta pluses, delta minuses, and so on. Okay, next, describe the trend in electronegativity as you go across a period. It increases. Describe the trend as you descend a group. It decreases. Which element is most electronegative? It's fluorine. Which factors must affect electronegativity? Okay, so nuclear charge. I think atomic radius or distance from the nucleus. Distance of, and remember here we're talking about electron pair, shared electrons from nucleus. And the last one is shielding. So very similar, ideas to ionization energy. Actually, less complicated than ionization energy. Okay, describe the trend in first ionization energy across a period. So it increases. That's the general trend. First, as you descend a group, it decreases. That shouldn't have been there. Why oxygen is more electronegative than hydrogen. Greater nuclear charge. So stronger attraction for bonded electrons. Now, there's more shielding in oxygen and a greater atomic radius, so we're just going to ignore that, right? It must be the nuclear charge. Oxygen has greater electronegativity than sulfur, despite having fewer protons. Oh yes, there's less shielding. Smaller atomic radius. So greater attraction for bonded electrons. Let's check the term they're using here. They're the same bonded electrons. Yeah, bonded electrons, that's okay. Or bonding electrons. Okay, explain why N2 is not an example of polar covalent bond. Same atoms, same electronegativity. Okay, and same attraction for bonded electrons. Explain why this is an example. The fluorine in HF is more electronegative. So it has a greater attraction for the bonded electrons or bonding electrons. It ends up with a partial negative charge, and H has, I'll just give it the shorthand, it has a dipole, so it is polar. You can see I am fond of writing loads and loads of good detail. Okay, why are there no electronegativity values for those included, right? The reason is they do not form covalent bonds. So electronegativity cannot be measured. Okay, next one. So then we're talking about polarity molecules, right? So what I said was that what you want to look for is a molecule with polar bonds and a lone pair or more is very likely. You can assume it is a polar molecule. Okay, so let's have a look at these. I'm just going to draw the shape. So PF3. Okay, so that's trigonal pyramidal. It has a lone pair, right? And it has polar bonds. Okay, so yes, it has polar, yes. And we say it's asymmetric. You don't really need to explain why. All you have to say is if it has polar bonds and it's asymmetric, then it's going to be polar, right? CH2F2, this is actually the brahedral ones that are an exception. Now, if it's tetrahedral and doesn't have four of the same type of bond, it is going to be asymmetric, right? So this is actually one of the ones to watch out for. It's only like something like CH4, well, which is non-polar anyway, non-polar bonds. CF4, CCl4, any of those are going to be symmetrical and non-polar. But this does have yes, and yes, it is asymmetric. So just if it is tetrahedral, right, if it has different bonds, different atoms, right, greater than 2, about greater than 2 different atoms, then it is also going to be asymmetric. Okay, BR2, no, no, right, no polar bonds. Right, so you don't have to, if it has no polar bonds, it can't be polar. It's only if you have a yes here, you have to think BCl3. Okay, so yes, it has polar bonds. And no, right, that has no lone pairs. Okay, so you can assume it is symmetrical. So it's a symmetric molecule, should write in there. Okay, CF4. Okay, it does have polar bonds, but they're all the same. It's symmetrical. The dipole moments cancel out. Okay, don't worry, as I say, it's really easier to just spot them rather than try and work out on the day whether the dipole moments cancel out or not. I think that's again vectors in 3 dimensions. You don't know. Okay, CL. Right, yes. Yes, it is, because it only has one bond, right? Yes, it's asymmetric. Okay, so if it only has one bond, then it has to be polar, right? One polar bond must be polar. Okay. Now, draw diagrams. Can I get this done on time? Okay, so I'm going to do this on the whiteboard. So this is question 1. Right, HF. That's A, B, C, D, E, and F. Okay, so they're asking here for A, polar or not, partial charges, polar, what is it, polar molecule, right, so yes, no, non-polar, yes, it's tetrahedral, but not all the bonds are the same. So actually the dipole moment will be like this overall, right? It does have, yes, yes, polar bonds, but it's non-polar because it's symmetrical, right? No lone pairs. Yes, polar bonds. Yes, polar, because it has a lone pair. Right, again, the dipole moment will go like this. This thing here, maybe I've taken a shortcut here. You might have drawn out your carbons, right? CH bonds are non-polar. This is a polar bond. And effectively, it only has one. So if it has only one polar bond, it is a polar molecule. And then question 2. Oh no, I'm not done. And G. BCl3 is, I'm not going to draw them, I'll just write the answers to these. Okay, it's trigonal planar, so it's not polar. CXCl3 has different bonds, so it is going to be polar. Tetrahedral. CH2Cl2 has different types of, has more than 2 different atoms, right? So it is polar. BR2 has 2 of the same type of atoms, so it is not polar. Okay, question 2, pick the type of bonding. So iron, metallic, covalent, covalent, ionic, ionic, covalent, covalent. Which of those substances would you expect to contain polar covalent bonds? Silicon tetrafluoride and carbon monoxide. Okay. Data bond. Okay, I'm going to skip that because you've seen that one already. Right, well, I suppose I should say it. Dot and cross diagram, so it ends up as trigonal pyramidal. Part B, suggest and explain the shape, right? It's got 4 electron pairs, 1 lone pair, 3 bonding pairs. And the shape is adopted to minimize repulsion between them, and the bond angle is going to be 107 degrees. So it's less than 109.5 you'd expect, because the bonding pair, lone pair repulsion is greater than bond pair repulsion. Is it a polar molecule? It doesn't count actually, because it is actually ionic. It has an overall charge. So if it has an overall charge, then it's actually a molecular ion. Okay, so no, actually, no, it's not. All right, explain, consider molecules are not example. Cannot be considered molecules. Okay, so they're ionic, because they're ionic compounds, right? So they don't have any covalent bonds. Which of the following molecules does not contain a polar bond? Fluorine. Which of the following molecules contains the most polar bonds? HF, right? So anything bonded to fluorine should be your first spot, followed by oxygen, followed by nitrogen, and then this has no polar bonds at all. Okay.